All right. So today for MDE 54, we're going to just do some more examples, and a little bit more of an explanation for graphing lines, using slope to graph lines, all those different features that we talked about in 154. And we're just going to go ahead and dive right into that. We're not going to do any kind of extra homework problems or just kind of sit and let you try things out. It's just going to be just straight through today, just so you know.
If you get caught, then you have the YouTube recording to watch. Yeah. So, as a reminder, we can take that font back down to a normal size, can't we? All right. So, for graphing lines, we need at least 2 points. We can use 3 points, we can use 4 points, you can use 5 points. It doesn't really matter, but we need at least 2. Now, when I say we need at least 2 points, that doesn't mean you have to be given 2 points. You could be tasked with finding them, or you could use 1 point and the slope. And that was something that we were heavily emphasizing in today's class, in my class, that is to say. So, or we need 1 point and the slope. That's the or. We either need 2 points or 1 point and the slope. If you are going to use the slope, make sure it is written as a fraction, even if it was a whole number first. So if it was 5, write it as 5 over 1. If it was 7, write it as 7 over 1. If it was negative 14, write it as negative 14 over 1. This is so we can see the rise and the run. The bottom number, the denominator, all right, denominator, and bottom, tells you how far to run, how far to run to the right, ever left. Write as many evers as you like. And the numerator, the top, tells you how far to rise, which can be fall if it's down, up or down based on the sign. So plotting 2 points is pretty easy. Plot the first point, plot the second point. Now, if you have some difficulty knowing which number tells you the left or right and which one tells you the up or down, that's another case of you just have to practice it. If you've only done it once before in your life, you're not going to do well. If you do it 20 times, you're going to do it well. You have to take the initiative. You have to put in the time. You know me, I'm going to keep saying that stuff. It's all about effort. It's all about practice. It's all about perfection. So again, with a point, it always goes x, comma, y. The first number tells you how far left or right to go. I can make that a better R. The second number tells you how far down or up to go. And whenever you're plotting a point based on its coordinate pair, you're starting at the origin. But whenever you're finding a point based on its slope, you start at the first point. So you will plot the first point and then go right and up, right and up, right and up, or right and down, right and down, right and down. All right, so for our first example, we're going to, I don't have to use my pen. Graph the line going through 1, 3, a slope of, let's go with negative 4. So when you're doing this by hand, you'll have to actually make your axes. In my math lab, they'll be set up for you automatically. Same homework and tests. There we go. All right, so here's our x-axis, here's our y-axis. Now doing this by hand, you got to figure out exactly how far left, right, up, and down you got to go. A lot of times what I'll do is just plot this first point of 1, 3, which is right 1 and up 1, 2, 3. and then I'll just figure out how far I need to go from there. So that way I don't have to label 50, 60 numbers in each direction. So there's the 1 comma 3, that's this point, the 1 comma 3, right 1, up 3. And then from there, we have a slope of -4. Now, -4 is not written as a fraction. I said to write it as a fraction even if it was a whole number. So how do we make a whole number a fraction? Put it over 1. And the denominator or the bottom tells you how far to run. Because remember, slope is rise over run. We call that a rate of change, rate meaning fraction, change meaning subtractions. I'm not actually finding a slope here. I was given it, but I'm just reminding you of those definitions. So the bottom number tells us how far we go right, never ever left. And the top number tells us how far up or down to go. And we said it's based on the sign and it should make sense. Up is positive, down is negative. So we'll go down 4. Now, most people will go right 1 and then down 4, but it doesn't matter. You can go down 4 and then right 1. But if you go right 4 and down 1, or down 1 and then right 4, that would be wrong because you have to pair the direction with the correct number. So we got to go right 1. So from an x value of 1 to 2. So here would be 2. 1, 2, 3. I'm just going to put these kind of to the side. 1 and 2. I know I wrote this kind of small, but that's because I'm going to end up writing over it if I don't. So I go from the first point we plot, not from the origin, because we're using the slope. We don't go back to the origin. We stay at the point. And we run 1, and then we're going to quote rise, which will feel more like a fall, down 4. Now, not down to -4. We started at a height of 3, so we got to count down 4. 1, 2, 3, 4, and that would put us at -1. And then there is our second point. And then all we do is form our line, which my math lab pretty much does for us automatically, unfortunately. And there's our line. But Excel will make our line for us as well pretty easily, as we'll get to on another day. Now, again, the slope, if I want to find a third point, I can go right 1 and then down 4, and then I can go right 1 and down 4, and I will always be on that line. It's a constant rate of change. That's what that means. But we only need 2 points because then the rest of them would still be on the same line. All we're doing is just acknowledging the fact that it's the same line. All right, let's try another one. Graph the line through -2, -5, slope 7. So we're going to plot that -2, -5. I could have done better. Label our axes doing this by hand. So -2, -5 is left 2, and then down 1, 2, 3, 4, 5. So here's that first point. Now, if I gave you another point, you would just go back to the origin and then move in whatever directions it suggests. Like if I said the other point's 1, 3, you'd go back to the origin and go right 1 up 3. It's not the case though. I said there's a slope of 7. But we need that slope written as a fraction so that we can see the rise and the run. The bottom being the run, so that tells us how far we go right, never left. If you had a teacher that says you can go left, admittedly you can, but it flip-flops everything and I just don't want to teach it that way. But per usual, if you have a method that works always, you can use whatever method you like. And then the 7 in the top tells us how far up or down to go, but since it's positive, it's going to be up. So from any point on the graph, we can go right 1 and up 7, or up 7 and right 1, and we'll get another point. So let's try it out. If I go right 1, I'm starting at -2, so I end up at -1, and then we're going to go up 7. If we start at a height of -5, that's 1, 2, 3, 4, 5. We end up at the at 0, a height of 0 after 5 of them, but we still got to go up 2 more. 1, 2, 1, 2. That spacing might not be perfect, but that's okay. We're not going to worry about that detail. And there we go. So that was -1, 2 is where that point ends up being. Now, if you don't believe me that it doesn't matter the order you go up and right or down and right if that was the case, check this out. If I go up 7, I'll go from a height of -5 to a height of 1, 2, 3, 4, 5, 6, 7. And then when I go right 1, I go from an x position of -2 to -1. The same point. That's an arrow. I mean a check mark, not an arrow. As I said, it doesn't matter if you go right and up or up and right. That particular order doesn't matter as long as you have the up paired with the 7 and the right paired with the 1. If you go right 7 and up 1 from this point, right 7 and up 1, you'd end up somewhere in this ballpark, and that would not be correct. So then we just connect our line and extend it. And there we go. Remember that slope is a measure of steepness. And the steepness, the steeper the line, the larger the value of the slope. Now, drawing these by hand, I could scale these, which means I could shrink or blow up one of the axes as much as I want and make these lines look about the same steepness, but in opposite directions. But in general, the larger the number, the steeper the line. So if you had a slope of, say, 1, if this line, without any sense of scale, if that slope is 1, maybe this slope is 2, and then maybe this slope is 3. Let me go a little less drastic on the middle one. It's pretty accurate, but there we go. So you can see these are getting steeper and steeper as the slope climbs. And what's interesting is it doesn't take a very large number for the slope to actually look pretty extreme. Like this one was a 7, and that is growing very, very fast in appearance. But it's all about scale. If we're talking about a problem where 7 is not really considered a large number, then this might look a lot flatter, potentially. Again, I can do that by just making these y values instead of -5 and 2. I could say this point right here is 20, and then that line is going to look a lot flatter because of that, because I've rescaled the y-axis. This isn't an issue we really need to worry about too much in the course, but it is something that can come up in the media. One news company might show a graph that looks like this, and it's accurate based on their scale. And then another company might show their graph looking like this, and based on their scale, it's accurate. And that's just because they scaled it differently. This one might look scarier, or maybe this one looks scarier if we're talking about financial growth. We'd rather see steeper than flatter. But again, that's how media can portray things. And when you are creating your graphs in Excel, you can kind of do the same thing. You can choose to change how wide or how tall your axes are. In other words, how quickly you get to 10 or 100 or 1,000. And then you could make your graph look steeper in appearance or flatter in appearance. All right. I said erase. Why didn't you erase? There we go. All right. Let's do another one. Graph. My caps lock is on, isn't it? There we go. Graph the line. Going through, no, let's go with, yeah, -2, 1. Slope, 5/2. So 5/2 means 5/2, 5 on top of 2. Your slope. So we plot our point, which would be -2, 1. So left 2 and up 1. Left 2 and up 1. There's our first point, the -2, 1. And then our slope is 5/2. So that's already a fraction, so we don't have to change anything. The bottom tells us how far right to go, and the top is up or down. Up since positive. So we're going to go right 2 units, -2, -1, 0, and then we're going to go up 5. If we start at a height of 1, we're going to have to go up to 2, 3, 4, 5, 6. Just extend my axis a little more. And it might be a little tougher to see, but that's not too bad. And then here is your other point. That point would be 0, 6, because you go left to right, 0 and up 6. You connect and extend, and there we go. I kind of wrote it over the instructions, but that's all right. So again, that point right there would be 0, 6, if you needed to see it as a coordinate pair. Let's do another one, but I'm going to phrase it a little differently. Graph the line going through, graph the line, an initial value of 12 and a slope of -5. Now, initial value, and if you aren't my student, you might not have heard this part yet, but another way of saying this is a fixed value. So initial or fixed is an alternative word for initial. So we talked about how our linear equations have a variable amount and a fixed amount. So any standard linear model is always a total equals a variable amount. I'm abbreviating variable amount plus a fixed amount, which we said is some number times x plus another number, which we started calling that mx plus b in the second section of the course, where m is our slope, but it's also our variable rate. And by variable rate, I mean the thing that has a per in it, like our tickets cost $2 per ticket. And then the b, that's the fixed or initial amount. Also known as the y-intercept. You can't tell the x-intercept in the equation. You'd have to just set the whole thing equal to 0 to find that. And we'll talk about that a little bit more later. So graph the line with an initial amount of 12 or a fixed amount of 12. That's the y-intercept, which means it's where it crosses the y-axis. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we go. So there is our first point. That's what I mean by an initial value of 12. It's where it crosses the y-axis, which can also be interpreted as the fixed amount or initial amount depending on the concept of the problem. If there's a slope of -5, that says that your slope is -5/1, which means you'll go right 1 and down 5 from that initial point. So maybe this is like every year we lose 5 of whatever this thing is. We started out with 12. Maybe we started out with 12 glasses, like a glass you drink from. We started out with 12 glasses, but we're clumsy, and every year we break 5 glasses. So that's kind of an interpretive problem here. We have 12 glasses when we move in or when we first buy a home or apartment or whatever, but every year we're going to break 5 glasses. So 5 glasses per year would be our rate, and because we're losing them, it's negative. So x is representing our years. So when you go right 1, so this will be us going right 1, and then down 5. So from 12, we're at 11, 10, 9, 8, 7. And there's our second point. And this line would represent any point in time how many glasses we have. So 1 year in, we got 7. If you want to know how many glasses do you have 2 years in, you can use the slope and go right 1 and down 5, and you could tell that 2 years in, we would have 2 glasses remaining. And then you might say, what about 3 glasses? So right, I just want to demonstrate that. Right 1 and then down to about there. That would be our 2. There's our other point on the line. Sorry, it's not perfect. And then after you go further, you go right 1 to 3. When you go down 5 more from a height of 2, you end up at -3. And I'm doing that one in blue for a reason, and I'm not actually on the line because of poor artistic ability. I can see why that is. They're just scaled too much. 1, 2, 3. There's our -3. Much better that time. And the reason I did that one in blue is, for the context of the problem I've said out loud but did not write, could we have -3 glasses, excuse me? No. The least amount of glasses we could have is 0. So at some point between when year 2 started and ended, we broke our last 2 dishes and we need to go back to the store and buy some more. Maybe we need to realize, well, let's try and break less. Maybe that's not controllable just because of who we are. We're clumsy. Some people are just more clumsy than others. Maybe you got kids and they're the ones breaking the glasses. I know some of y'all can relate. But yeah, that's another one of those cases of where I was talking about before, how sometimes a mathematical model will stop making sense because something happens in the real world that makes things change. And like I said, if we're modeling the number of glasses we have, once it goes into the negative, that model doesn't make any more sense. Now, what I have purely typed up as a pure math problem, there's nothing that says nothing makes sense. We can just keep going right 1 and down 5 forever. But just understand, context of problems can change some of those things like that. You know, negative, you don't really talk about negative time or negative tickets or negative a lot of things. Money we can talk about negative. We definitely have positive and negative money. We have debt and growth. So that's okay. Time, negatives, not really. Number of items made, negative, not really. All right. And then finally, I just want to say that point up here at 12, that was 0, 12, if you didn't pick that up. And y-intercepts always have an x value of 0 because this line right here always represents x being 0 because you're not moving left or right on it. All right. Well, this slope that I've been giving you, what if you had to find it? So as a reminder, your slope formula, which I already wrote that it's rise over run, which is a rate of change. So y2 minus y1, that's the change of the y values, new minus old, over the change in the x values, new minus old. I will admit the new minus old aspect is interchangeable. You can do old minus new as long as you're consistent. You can go old minus new, which would be the 1s minus the 2s. Because the top would change sign, the bottom would change sign, and 2 things changing sign cancels each other out under multiplication or division. But you have to be consistent. You can't do 2 minus 1 in the top and 1 minus 2 in the bottom. You got to make sure the y values, the heights are in the top, and the left or right values, which are the x values, in the bottom. All right. So find the slope of a line going through -1, -5, and -2, 12. And that's all I'm asking for, not asking for the graph. If you wish to label things, which I suggest at first at least, the -1 would be your x1. And inflection in voice, the -5 would be the x2? Question mark, question mark, question mark? No. Remember, coordinate pairs always go x, y. That's a very easy thing to make a mistake on, but that would be the y2, right? No, I'm messing with you again. I know I'm mean that way. It's y1. I don't think I'm mean, really. I'm being silly. It's more about the pay attention factor here. And the -2 and the 12, that would make up our, and I'll even do them in different colors for good emphasis here, our x2 and our y2. So for our slope, we just got to put 4 numbers into a formula, and hopefully we don't need a calculator for this, even though it's at our disposal. If these were bigger, crazier numbers, sure, we can pull out the calculator, but not for this. So y2 minus y1, so that's the blue one minus the red one, but specifically the second values in each parentheses. So 12 minus -5. Notice what I just said. 12, and this this is the minus that's part of the formula. That minus in black is the minus in the formula, but then the y1 is a -5. If I just do this, it doesn't look so hot. Most people would do it this way, and I would make that suggestion. But what happens is a lot of people end up missing this negative because they see the minus and they think that minus goes with this minus, but no, it doesn't. That minus was part of the formula. Then the y value also had a minus. You have to be careful. Then over, subtract the x values. Be consistent. Since I went 2 minus 1 for the y's, I got to go 2 minus 1 for the x's. And not literally those numbers, I mean the second one minus the first one, which is -2. So that's the blue one. Then the minus for the formula. And then the x1 is -1 because it's negative. Same issue. I did that intentionally. Go ahead and get us used to it. Double negatives mean change it to addition. So that's 12 plus 5 and -2 plus 1. 12 plus 5 is 17. -2 plus 1 is -1. But anything divided by a positive divided by negative is a negative. We don't really like a negative being left in the bottom. We also don't need to leave a 1 in the bottom. That's just -17. That's our slope. Now, when you put slopes as answers in my math lab or say them to someone, you are supposed to make them whole numbers if they're whole numbers. You only use this for graphing. And I'm gonna put a little asterisk next to that because I don't like the negative in the top. I would prefer that to be in, I don't like the negative in the bottom. I would prefer it to be in the top. So really it should be -17 over 1. However, most people would still understand that you're going right 1 and then because it's a negative down 17. But some people will misconstrue that that means you're going to go left. And I already said from the perspective I teach, there is no left because it flip-flops every single aspect. Flip-flops are when people end up making mistakes, not the literal shoes. It's just too many things changing all at once can make mistakes. And I had another point to make and it just escaped my brain. What was it? Now I remember. Okay. Alternatively, I'm going to do this same exact problem again, but I'm going to prove to you by example that the order of the 1s and the 2s doesn't matter as long as you're consistent. The y's have to go in the top, the x's go in the bottom. But now I'm going to do the 1s minus the 2s, or you could pretend I called the first point the second point and the second point the first point. That's another perspective you could take. Because there's nothing that rigidly says, hey, this is the first one, this is the second one, it's just the order they occurred. If we're talking about an example, it might make more sense to call that first and second. And actually, I would say in a real world example, I'd probably flip-flop these and call the right one the first and the left one the second. Because graphically, that's the order they occur. And I'll graph it at the end just to show that. All right, rambling aside, now I'm going to do the 1s minus the 2s. So I'm going to go red minus black. So for the y's, I'm going to go -5. That was the y1. Then minus the y2. That should have been in black. And then the y2 was the 12. No double negative that time. That's cool. In the bottom, we're going to go x1 minus x2. -1 minus -2. Well, that is a double negative this time. -1 minus the -2. So that just happens again. Let's fix this up. That's -5 minus 12 over -1 plus 2. -5 minus 12 is -17. Same sign, add the numbers, keep the sign. -1 plus 2 is +1. Same rules. And that's -17. The same answer. You want to see what this would look like if you did it wrong? And I forgot to change a color here. That was supposed to be blue. Sorry about that. See, last time I did reds minus, or first time I did blues minus reds, second time I did reds minus blues. Let's see if we do this wrong. Let's say we're just throwing caution to the wind and not caring about the order of the 1s and the 2s. So in the top one, I'll do y2 minus y1. So y2 was the 12 minus y1 was the -5. Then over. So I'm going to go 2 minus 1 in the top, but I'm going to make a mistake, and I'm going to do 1 minus 2 in the bottom. I'm not going to be consistent. So I'll do -1, that's the x1, minus -2, which was the x2. See, the color is showing you I wasn't consistent in the order. That's 12 plus 5 over -1 plus 2, which is 17 over 1, which is 17. And that is, again, wrong. It is, in fact, the opposite of the correct answer. And the interesting thing is, whenever you do that, you'll always get the opposite of the correct answer. Now, if you start subtracting a y and an x and an x and a y, I don't know what's going to happen. All sorts of weird things are going to happen because you're making a much more significant mistake. But it doesn't matter if you do 2's minus 1's or 1's minus 2's as long as you're consistent. You have to put the y's in the top and the x's in the bottom. If you flip-flop them, this answer would have been -1 over 17, which is what we call the reciprocal of the answer. And that kind of relates to how we said with the y equals kx version of proportions. Depending on which one you call the x and which one you call the y, if your constant of proportionality is 5 for one of them, it's 1/5 for the other. It's always the flip of it, the reciprocal of it. All right, so finally we said we were going to graph this. I'm going to put the graph down here. I'll pull back after. What are our points? What are our points? -1, -5, and then -2, 12. -1, -5, -2, 12. Let me just go ahead and do it this way, so I don't make a silly mistake. Sorry, that's really far out. -1, and then comma -5. So we're going to go down 5. 1, 2, 3, 4, 5. So here's that first point. I'll even do it in red for emphasis. And then the second point is at -2, 12. So we got to go left 2. That's a little too far. And then comma 12. So that's up 1, 2, 3, 4, 5, 6, 7, 8, 9. Got to go a little more. 10, 11, 12. All the way at the top there. And we'll do that in blue so it represents the second point. And then you just connect and extend that. If I hit enter, will all that go down? No, it won't. That looks awful. Maybe if I do it up here. Boom, sweet. I just want to make that a little better. Because it was starting to get a little squirrely. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That looks better. So -2, 12 is all the way up here. And then we just connect and extend. I'll do my best straight line I can without taking an hour to make it. Oh, that got bad at the end. One more time. Nope. 17 more times. Let me just connect from point to point and then extend. That might help me. Nope. Nope. Zooming in would definitely help. Okay. I swear I'm a lot better at this when I'm not using a blind tablet. Boom. Good enough for government work. So we can see that from this point to this point, we're going to go right 1, which is not very far. Let's just pick another color. Let's go with green. We'll go right 1 and then down 17. From 12 all the way down to -5. That's a 1, and that's a going down 17. You end up making these little right triangles whenever you show that. Do you have to show that? No. Should you show that in your My Math Lab homework or test? Not unless they ask, which I don't believe they do. But it's a great way to learn when you're doing this on your own on scratch paper and such. And of course, label your axes, X and Y. All right, the next set of things I want to do is I want to have us practice creating a standard linear model. All right, write the equation, linear model, a company that has a rent for a company's expenses. They're solely rent being $3,000 per month. Or let's just say $3,000. I'm going to go back and edit this. Write the equation for the linear model of a company's monthly expenses, where the rent is $3,000 and they spend 50 cents to make each unit. I didn't say what they're making. I just said it costs 50 cents to make them. Now that 50 cents includes the cost of materials, the cost of labor, et cetera, et cetera, et cetera. All of that is just tied nicely into it. Now in the real world, you can't always just say it's a flat 50 cents per unit to make something. And to make each unit is another way of saying per unit. So that's the same as saying 50 cents per unit. I'm doing that intentionally because I always emphasize the word per, meaning the rate or ratio or the slope, but I didn't actually use the word per in here, so we have to understand that in the real world, words are not always consistent. There's other words to get the same job done. So we have a rent of $3,000. Now that month's rent is not changing until maybe another year or two from now, in which case the model would change. As I've said, models can change eventually. And then it's 50 cents to make each unit. So if they didn't have rent, if they were just doing this in an open field for free, then they would spend 50 cents to make one item. They'd spend $1 to make two items. And again, that's including employees, compensation, cost of materials, all that stuff. Then they'd spend $1.50 to make three items. They'd spend $2 to make four items. They'd spend $5 to make 10 items, et cetera, et cetera. But they got to add in that $3,000 worth of rent because they're not in a field somewhere. They're in a nice air-conditioned building, hopefully air-conditioned. In a factory, maybe, maybe not, but that's besides the point. All right, so once again, let's remind ourselves of what we said earlier. All this right here. The standard linear model says that a total amount is the variable amount plus the fixed amount. Or you can write it as mx plus b. Some people say ax plus b. The letters do not matter. It's something times your input variable plus a fixed amount, plus a number. It's a number times an x plus a number, or a number times a t plus a number, or a number times a q plus a number. Whatever your variable you choose is. So we're saying that the total amount of expenses, let me write that more specifically, total monthly expenses should be the variable expenses plus the fixed expenses. The fixed amount doesn't change. I'm just going to abbreviate total monthly expenses. The fixed amount does not change. Rent is not changing. There's no per here. It's not based on, if I do more of something, the rent goes up. You just pay that flat $3,000 bucks. But the amount that we spend on the units, the CDs, the calculators, the buckets of water we're making, whatever it is, they do cost, and we pay our employers to make them as well. And that comes out to a nice round number of 50 cents. Now, if you want your total monthly expenses to be in dollars, which is what I'm demonstrating here, that 3,000 is the dollars, I can't do 50 here. That would be wrong because now I've got cents and dollars and they aren't in the same scale. So I've got to convert that 50 cents to 0.5 or 0.50, whichever you like. I'm going to stick to 0.5. So 50 cents is $0.5, but of course. Now, if you write this, it's wrong. Your total monthly expenses is not 0.5 plus 3,000. Remember, the variable amount has to have a variable. So you can use whatever letter you like. I usually like X. You could use U for units. If we knew what we were making, like CDs, I could write C, or Q for quantity. You can argue about any letter in the alphabet. Don't ever use O. Please don't use O. It's a horrible letter to use. I think you can figure out why. So this is our equation. And I could say that this is okay. It's okay, but it's not great in quantitative reasoning sense because I have not declared what this variable is. I have not said specifically what the total monthly expenses are in as a unit. So I need to say that X is the number of units made or produced, and then the total monthly expenses is in dollars. Now what we have here is a perfect standard linear model. I could even graph this. I didn't ask for the graph, but I'm going to graph it. Yeah, we'll just do this. Again, kind of scale out. I wish I could just go no gap in pages. So we have an initial amount or a fixed amount of $3,000. Now I'm not going to make very much of the negative side of these things because we can't make negative units, so it doesn't make sense to go on this side of the graph at all. And if it costs $3,000 if we don't make any units and making more costs more money, we're not going to see any graph down here either. Everything's going to be positive. So $3,000 is how much that first unit costs. And I'm going to decide to put 3,000 about here, which would make 1,000 about here. Sorry, 2,000 and then 1,000 about here. See, I'm not scaling by 1 here, I'm scaling by thousands on the y-axis. But on the x-axis, since I've got 50 cents per, I can certainly just scale them as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, et cetera, et cetera, et cetera. So I can certainly go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 if I wanted to. So we have our first point, which is here. That was the initial or fixed amount, our y-intercept. That's our rent, and we're not making any units. And then I'm barely going to be able to show you this because of the scaling. And that's the reason I'm doing this. I'm going to do it once and I'm going to do it again. Our slope is 0.5, which is a fraction is a half, which says you go right 2 and up 1. But I don't really have a very easy way of showing where 3001 is. I can very clearly show to go right 2. And that looks pretty good. That's about right 2. But going up 1, I mean, if that's 3,000, I know you can barely see it. I mean, I barely moved. I'm going to call that 3001, and even that's an exaggeration. So then here's your second point, and your line ends up looking like this. I mean, it's practically a flat line. And that's because making one more unit at a time does not really bump up the cost for the month that much. Making one unit is now $3,000.50. Making 2 units is now $3,001. Every 2 units we make is going to bump it up another dollar. So what someone might say is, well, I don't want to scale this based on 1 versus 10. Let me scale this in hundreds or thousands like the other side is. So an alternative graph might look like this. I'll still go in thousands on the y-axis. 1,000, 2,000, 3,000. So that's our y, which is our cost in dollars. And then this was our x, which was our units. So maybe you want to go 100, 200, 300, 400, 500 units. Maybe you want to go 1,000 units. 1K, 2,000 units, 3,000 units, 4,000 units. So with a slope, so here's our initial point at the 3,000. With a slope being, we said it came out to 1/2 every time we go right 2 we go up 1. I don't really see 1s and 2s up here. Sorry about that. So what we can instead do is just make this in thousands. Since this is in thousands, this is in thousands, this would be equivalent to having 1,000 over 2,000. So every time we go right 2,000, we're going to go up 1,000, which means I'm going to need to have a height of 4,000. So I'm going to go right 2,000, and then I'm going to go up 1,000 units. There's our second point, and here's the line. Now please understand, this is the same exact line as what you see above it. They're just scaled differently. That's what I was talking about, how maybe media can misrepresent information by just choosing a scale completely differently. Now, which one's better? I mean, it just depends on what kind of perspective you want, but they're both accurate. It just really shows you that life can be all about perspective. When you look at the top one, it looks like there's an insignificant change. When you look at the bottom one, it looks like the change is more significant. However, it is literally the exact same. It's just a matter of scaling the number of units to be exactly the same spacing as the cost, or not scaling the number of units as the same spacing as the cost. Now, when you do something in Excel, it's going to automatically scale something, and maybe it makes it look like that. But what you can go back in is edit the graph in all the Excel ways that I'm not going to sit here and talk about for 15, 20 minutes. Go back to the beginning of the semester for that. And then you can make it look flatter, or you can make it look steeper. But if you actually write the equations out there, which I will be demonstrating in my class on Thursday, this one would say y equals 0.5x plus 3,000. And this one would also say y equals 0.5x plus 3,000. Same equation, same information, same application, just a different picture based on scale. It's kind of like if I put a big problem on a whiteboard in class, and I said, all right, I want you to take your nose, and I want you to put your nose literally on the whiteboard, and I want you to read that problem. You're going to have a much harder time seeing it because of your perspective. But if I ask another student to step back maybe 10 or 15 feet and read the problem, they're not going to have any issues with it. Now, is it always a case of one perspective makes it impossible to understand and the other doesn't, and the other makes it super clear? No, I'm just trying to give you examples of how sometimes things just look differently because of your perspective. When we start getting into curves, when we start getting into exponential functions later, we're going to start graphing things that look like this. This is spoilers for chapter 6, which is not that far off. So this is called an exponential equation. And it's going to be the main theme of chapter 6 and on. And it bends. It's a curve because it bends, and it should start at the y-axis. And maybe it starts at 0, maybe it starts a little higher. It just depends on the model. It depends on the point. But check this out. I don't know how far I can zoom in on Word. Let's see. So it looks nice and curvy. But look what happens as I zoom in. Every time I zoom in a little, it moves. It doesn't let me zoom in any past this. But when I'm looking at this, I don't see the whole picture anymore. I only see a portion of it. And you can see a lot more of my imperfections. But just this little segment doesn't look nearly as curvy. You can't see all of that. Come on. You just see this, which almost looks like a line. It almost looks like a line. When I'm looking here, you can see the bendiness of it, but the point is, I can't zoom in quite enough with this program, but what I'd like you to do is pretend like I just took this little segment and I zoomed in. So this is me putting my nose to the whiteboard. So This is the zoomed in portion. I'm going to put it a little on the left, actually, because I'm going to do this twice. That zoomed in portion, which I'm not going to show the axes, is just going to look like that. You might think that looks a little more bendy than this, but again, if you really zoom in on just that portion, that really does just look like a line. Come on, come on, there we go. Or if I zoom in, you might say, okay, well, this part over here, that looked really bendy when you zoomed in earlier. So let me just zoom in on that portion. And it doesn't look like the same line. It looks like a steeper line. Maybe something like this. But it still looks like a line. No matter where if you zoom in on a really small section of this anywhere, this curve that bends, that goes from being pretty flat to then all of a sudden just drastically taking off, and I like to use the word exploding quite frequently, as you'll hear, you can't see that explosion when you put your nose to the board. You're at a different perspective. And this is the concept of taking a mathematical model on a shorter or longer time scale. If you consider this maybe a population over 100 years, it's a pretty solid model. But if you only want to look at the population for 5 or 10 years, it's actually pretty easy to approximate it with a line, no matter where you are in that model. But if you want this whole 100-year segment, you can't approximate this with a line, because show me a line that's going to be pretty accurate looking in comparison. And again, the really interesting fact that we don't study in this course is if you zoom out to 1,000 or 2,000 years instead of just 100 or 200 years, even this model falls apart, because you start seeing this kind of growth. You get this explosion, but then you get a taper off eventually, because there are things that limit the size of our population, like how much space we have, how much food we have, how much water we have, clean air. So perspective not only changes the appearance of a model or of a graph, it can also change what model or graph to use. All right, so with that rant aside, which you'll probably hear me say that again in the next couple weeks, we'll go ahead and call it a day there. Yeah.
All right, so like I said, we'll continue on with our journey in chapter 5, dealing with these lines next time. We'll keep, upping the difficulty, looking at things from different approaches, all sorts of good fun. We'll talk more about the slopes and intercepts, but for now, take care and have a good day.